Let's take a look at an example where you are asked to write an exponential formula for data that is exponential. And let's take a look at two situations, one where the rate of change is increasing, so growing, and B, where the rate of change is decreasing or decaying. So we have a population of bacteria. Is 1,500 members when an initial observation is made. So imagine you've got a petri dish, and when you make your first observation, there are 1,500 bacteria in it. So I always tell my students to write down all the information that you have off to the side here. So this tells me that my initial population is 1,500 bacteria. And then in scenario A, we want to assume that the population is growing. So because it's growing, we know that this means that our growth factor is going to be 1 plus R. So you're always going to use 1 plus R when you have growth. And so let's write down what R is. R is 2.5% per hour. So go ahead and convert that percent to its equivalent decimal and make sure you do it correctly. And so now we can go back and actually calculate B. So B is 1 plus 0.025 or 1.025. So now that I have my A value and my B value, I can write my formula. So here, that formula would be the population of the bacteria is equal to 1,500 times 1.025 to the T power. And then once you have that formula, you can calculate things like, oh, well, how much bacteria was in the petri dish after 8 hours? How much was in the petri dish after 10 hours? And then we can also ask questions like, how long will it take for, um, how long will it take for B of T to equal, okay, so how long will it take for it to become, 3,000 bacteria? So here, you know B, and then you're just working backwards to solve for T, okay? Let's take a look at question B, where we assume that the population, instead of growing, is decreasing. So same thing, write down all the information you have off to the side here. So I have 1,500 bacteria to begin with. But here, because it's decreasing, instead of having a growth factor, so let me use red here. So up here, B is called your growth factor, okay? In situation B, B would be 1 minus R, where here, because we're doing 1 minus R, this shows that we have a decay factor, which is what you use in the formula when your function is decreasing or decaying. So using the same rate, okay, 2.5% per hour, convert that to its decimal equivalency. And then here, our decay factor is going to be 1 minus 0.025. So if we put that into our calculator, and let me do that real quickly here, 1 minus 0.025, we get a decay factor of 0.975. So now we have all the information that we need to write our formula. So the formula here would be B is equal to 1,500 times 0.975 to the T power. And again, we can still answer the same questions like, well, what is B of 8? What is B of 10? And then here, because the function is decaying, we might want to know how long will it take for the bacteria to become half of itself. So what would be its half-life? So here we want to know what is T when B of T is, let's say, half of its initial amount, so 750 bacteria. So again, you have B and you're working backwards and trying to solve for T, okay? So one more thing I want to mention while we're here is notice that anytime you have an exponential function that is growing, your growth factor, so this B value, is always going to be a number that is greater than 1. But anytime you have a function, an exponential function that's decreasing, your decay factor in your formula, it's always going to be a value between 0 and 1. So it's going to be less than 1, but still always positive. So I really hope this helps.